Gerardo is very well known in the world. Many people know his work on basic quantum mechanics and quantum metrology and quantum information and everything like this. And today, Gerardo will talk about every quantum helps, which I'm actually curious to know exactly what is this. Gerardo, thank you very much. Thank you very much for accepting our invitation. I'm deeply sorry my camera is not working. I don't know.
It's okay. I remember your face. It's fine.
Okay. Thank you very much.
Thank you very much. Yeah.
Our invitation, and I mean, the screen is yours.
Okay, great. Yeah, I really hope that at some point soon I will come back to Brazil because I'm missing it. It's been a while now. Yeah. So next event.
By the way, can we ask you questions during the presentation?
Yes, of course. Yeah.
Okay.
Yeah, I might not be able to see the chat because of the way Zoom works. So if you just, unmute yourself.
No, the chat is okay.
That's fine. Yeah. No, I don't think I'm able to see the chat while I'm giving the talks. That's why better if you just speak. That's fine. Yeah. Okay. Yes. Thanks. So I'm at the University of Nottingham in the UK. This talk is a funny title, but I hope that at some point the meaning of this will become clear. Both from a physical and a mathematical point of view. So, yeah, so what is the idea here, right? As we all know, there's been, and there is an ongoing race for development of quantum technologies. And there are lots of claims that we are close or we have achieved so-called quantum supremacy. Now, this word has been contested, but I think quantum advantage is a little bit more acceptable to you. So in the specific context of quantum computing, there were big announcements, first by Google 2-3 years ago, and then more recently by Chinese Academy of Science, group of Zhang Weipan, about having reached this milestone of quantum advantage or quantum supremacy. But there are some, well, these claims are, of course, attracted lots of attention, but they're still contested for several reasons. So they specifically are about showing that some problems can be solved in a lot less time. So it's a lot faster to solve them on special purpose quantum computers, which are made of 50, 60, 70 qubits, compared to what are presumed to be the capabilities of our existing classical devices. Then, of course, on one hand, it may be that the computing power available at the moment is underestimated. And this is what happened with the first paper by Google. As you know, even before publication, there were researchers from competing companies like IBM claiming that what Google said would take 10,000 years to finish actually could be done in maybe 3 minutes, which is still more than the few seconds that Google took on its machine. On the other hand, another problem is these specific tasks that they are implementing to show quantum supremacy are kind of useless tasks. So they deal with sampling problems, which are sort of academic value, but they do not solve real problems that we need at the moment in practical application. So tasks like boson sampling, sampling probability distribution from random unitary circuits, they are such that you get advantages already with less than 100 qubits, so they're suitable for this specific moment of developing near noise intermediate scale quantum computing, but they do not necessarily address the main need for quantum computers in the first place. And then we do not have a conclusive benchmark to say, yes, we have definitely established an advantage, or we can quantify how much this is better than other classical protocols, even because we do not yet know what is, say, the upper bound on the capabilities of existing technology. So I think it's been very, very stimulating to follow this race, and this has given, I would say, inspiration to both the classical and the quantum community to do even better, and in the end, overall, to improve our technological capabilities. But there are more general questions that we can ask, and it is, so these quantum technologies, they run on some specific ingredients that are in the domain of quantum mechanics, but which ones are they? So what is behind the power of quantum technologies? There are lots of things that are branded as quantum, even out of context. Like there's a supermarket in the UK called Tesco, and they sell something called quantum dry deodorant, which I actually bought, and I don't know if it's any better than the classical ones. Similarly, you probably know quantum tablets for washing machines. And at the beginning of lockdown, when I was stockpiling on toilet paper, there were quantum quilts. I didn't find any advantage in using them compared to conventional ones. So the question is it the case that every time we have something that is definitely non-classical, it will help us in some task? So we try to give a mathematical answer to this question in this talk. But before we go there, there are some examples that we definitely know are useful. So one quantum feature that has been extensively studied, and we know it is behind the power of certain applications to quantum information communication, is definitely entanglement. Oops, sorry, what did I do? I jumped to the end. Wait a second. Okay, so entanglement is one such feature, and we can describe entanglement very, very simply if you want. Well, when I first heard about it, I was a graduate student, and I think this was the slide I used maybe 20 years ago, when I was just fascinated with the concept. So it is, as you all know, a form of quantum correlation between two or more systems, and it seems to defy the basic notions of relativity, because it seems that it conveys some kind of action at a distance, even though that is not the case. But the idea behind it is that when we have multiple components of a quantum system, then if there have been an interaction, they cannot be just considered as independent systems anymore. So overall, even if they localize, they maintain some correlation, which we know for sure it can be stronger than any classical means, for instance, as validated by demonstration of violation of Bell inequalities and so on. And you can see entanglement expressed in various forms, even outside of science. For instance, you can see people trying to convey the idea of these strong bonds in the arts, say in sculpture, in paintings. But what is really crucial about entanglement is that after being puzzling with that concept for many decades, community of scientists have eventually found a way to prove that it is useful as a resource. So there's been lots of little tasks where you can show that by using entanglement you get some advantage, and you can also have some general results. I'm quoting some of these here, where it says not just, you know, you have to prepare states in a certain form, but all entangled states are useful for information processing. In this specific paper, it was about assisting the teleportation power of other states. In the second paper, it's about channel discrimination, and this will become important for our talk. And then the last one is again straight to beat any benchmark for classical teleportation. So all entangled states are useful. So entanglement is a resource for quantum technologies. And whenever you have just a little bit of it, then you can do better than states without entanglement. That's what these kind of papers prove. Of course, entanglement is not the end of the story. So the quantum world might appear small, but it's a vast and dangerous world, still a lot unexplored. And I know maybe this picture, this specific historical moment is not very fortunate, because hopefully exploring the border, the quantum border, is not so much dangerous as what's happening in the world at certain borders at the moment. But this border is also contested in a certain way. So it's not clear how to establish when the quantum world ends and when the classical world begins. So what we've been doing in Nottingham for the past few years is trying to patrol this border and to understand what makes the quantum world quantum. So on one hand, what are the specific signatures that we can identify that definitely prove that what you're looking at cannot be interpreted in terms of just classical probability distributions. And we've done this a lot by looking even beyond entanglement at other forms of correlations or other forms of resources. And on the other hand, once we recognize features which are generally quantum, the question is, what can we do with them? Do they enable us to beat certain limitations that are affecting classical technologies, or can we actually untap the power of these as resources, you know, like it happens for entanglement, but also with other manifestations of quantum mechanics. We try to give an answer to this question in this talk. So how do we do this? It's by taking advantage of a framework, which is the one of resource theory. I'm sure that many of you have been working in this and are familiar with it, but I'll try to explain it in a kind of simple metaphorical way first, and then we go into the specifics. Suppose that, I don't know, your old great aunt passes away, and then you inherit a basement full of tools. So you're given this for free. So there's this complicated machine down there, you don't know what it does, right? Then you start to experiment with it, and then you see that, okay, if, just put the pointer there. Okay, yeah. So if you feed certain, I don't know, water or just substances that you do not consider of a lot of value into this machinery, then you do not get any useful result. But on the other hand, at some point you discover that if you input specific, in this case, liquids into your machinery, then you get some useful result. In this case, say you generate electricity. So this kind of metaphor is to say that this laboratory that you have inherited from your relative is what we would call free operations, something you do not have to spend money to implement. You're given them for free. And if you feed free sources into free operations, then you do not get anything out of it. So this will be the empty bottle here. On the other hand, there's been some precious resource that you can feed into the machine, and then you obtain some useful result. This will be what we call a resource. So mathematically, what we can do is we can look at the set of quantum states and the set of quantum operations, and then we can make some big distinction in them. So within the set of quantum states, we can identify a subset, which we call free states. They would be like the empty bottle before. They do not contain any useful resource. Of course, there are multiple ways of doing this, depending on what you consider to be the resource in this case. Say, if you think about entanglement, then your free states would be the separable states. And any other state which is entangled, it will be a non-free state, so something that you would call a resource. And then in terms of operations, you have the set of operations which are free. These are the ones that by themselves cannot create any resource, like this laboratory that you have inherited. For entanglement theory, this would be local operations and classical communication. And then any other operation, in this case, which has capability to create a resource, would be a non-free operation. So, for instance, what you can do then, if you start from a free state and implement just free operation, then you will end up into another free state. If you start from some resource state and you implement free operation, you cannot increase the amount of resource in the state. You can at most keep it the same or decrease it. And so it can even end up being a free state at the end if you have destroyed the resource content. On the other hand, if you start from free state but use a non-free operation, then you're able to create some useful results. So at some point you need to invest. Either you invest in non-free states and you just use your free equipment, or you have to invest in some non-free operation in the first place and then manipulate and then you can send in free states and then generate resources that way. So this general framework has been applied successfully to entanglement theory, and in recent maybe 10 years to a lot of other physical features of quantum mechanics and even beyond. So once you have this apparatus in place, then you can start asking questions which have a very nice formal answer. So for instance, questions about state manipulations, under which conditions you can convert some resource state into another resource state just by means of free operations. If you need states in a certain form for a certain task, you might want to just convert them back and forth, and you want to know whether this is reversible or irreversible, for instance. Yeah, so at some point you might want to condense your states into a less number of more resourceful ones, that's distillation, or you just want to dilute them away, on the other hand, into a larger number of weaker states that you can maybe still use in some applications that do not require so much amount of resource. And then crucial question is, how do you quantify the amount of resource in a state that is not free? what are the states that have the most resource, and what are they useful for? All these kind of questions would be nice if they had some universal answers. Unfortunately, this is not always the case, but the guiding principle of resource theories will help addressing these and related questions. Right, so we will concentrate, for instance, on one specific resource first, and then try to generalize to a more general structure of resource theories. And the main question that is not always easy to address is the one of operational interpretations. Yeah, we're talking about resources, but resources for what? What are these things useful for? And once you understand this, then of course you also are given some natural framework to quantify your amount of resource and relate it to the advantage it enables in some applications. So I will focus on quantum coherence first and give you two examples of operational interpretation. One which is indirect, let's say, and the other which is more direct. And then we will generalize the second one. As I said, I will focus on quantum coherence. Why? Because quantum coherence, I think, is just the beating heart of quantum mechanics. It's probably the simplest, most essential resource that you can consider, and it defines a difference between classical and quantum theory. So coherence means superposition in a given basis. And it is a central ingredient of more elaborate resources like correlations, including entanglement and other manifestations of them. It's been appreciated as a necessary ingredient for advantages in tasks, including sensing metrology, and it's been investigated a lot also in other contexts, like possibility of coherent effects in biology, the role of coherence for thermodynamical machines in condensed matter many-body physics, and so on. Right, so quantum coherence can be, strangely enough, has been formalized as a resource theory after entanglement, even though it should have come before. But we have learned from entanglement in order to characterize this even simpler resource, which is coherence. And what we know about coherence is, from the point of view of states, it is a super easy resource, because what we need first, you need to specify a basis. So this seems strange, but many cases the physics of the problem suggest which is the basis with respect to which you're going to analyze the presence or absence of coherence. For instance, I don't know if you're looking at energy conversion, then the eigenstates of the Hamiltonian would be your preferred basis. And then once you have specified the basis, then you can distinguish your quantum states into two classes. States whose density matrix is diagonal in that basis, these are incoherent, and states whose density matrix contains some of diagonal elements. These states would be coherent, so they have a certain degree of coherence. So the incoherent states, they are the ones which are equal to their diagonal, or if you want, they are invariant under full dephasing in the preferred basis. So this dephasing operation is specified by this capital delta. On the other hand, the free operations, it seems to be an ongoing struggle with it, because there are many different classes that we can propose, and I do not want to enter into this debate for the sake of this talk, but there's been historically several proposals to define free operations, each of them with some merits and each of them with some drawbacks in terms of physical interpretation or the operational power. But let me just mention a few classes. Of course, there is the largest possible class of quantum channels that do not generate coherence, and this we call maximally incoherent operations. And then there's been proposed several subsets of this class which have been defended in terms of having a better operational meaning in certain contexts. For instance, dephasing covariant operations are the ones which commute with this full dephasing operation. Then there are the incoherent operations proposed by Plenius group, and they are the ones such that the quantum channel can be decomposed in its Krauss representation, and each of the Krauss operators is maximally incoherent. So this means that those channels cannot even create coherence probabilistically. And then there is a subset of these two, which is called strictly incoherent operations, which seemed promising at the beginning. It's been proposed as channels that cannot create and cannot even make use of coherence, but then later on it's been shown that it is really too much of a restrictive class, because almost every state cannot have distillable coherence under this. So there's generic bound coherence under this operation. This is
Sorry,
something that, yes.
Gerardo,
Yeah.
may I have a question?
Yeah.
How big are these sets? I mean, because usually in a small perturbation will create coherence in any basis in the disk operator. So how big are these sets of incoherent operations?
They are all of full. Of course, they are all of full volume. While the set of free states is zero volume states. It's difficult to quantify the volume of them, but I wouldn't know how to do it in general in arbitrary dimensions. But you're right. So
are they convex sets or not?
yes. Yeah. Because we are even the set of free states is convex because we have specified the base. If you consider the union of free states with all possible bases, then it's not anymore. Well, once you fix the basis, then it's
okay,
fine.
Yeah. But the free states, I understand that they are convex sets. But the free operations, I don't know. I mean,
yeah, but
let us think about energy eigenstates. I mean, any transformation that generates transitions between these guys, between the energy eigenstates, will generate coherence.
Yeah.
So I don't understand. I don't understand the volume of these guys.
Yeah, they will be outside. Yeah.
No.
These are the free operations. They that do not generate. Yeah. Yeah, I don't know how to answer the question about the volume, but you're right. So they're not big.
Okay, thanks.
Yeah. Okay, so these are different proposals, as I said, and I don't think there's still universal agreement about which ones to use, but there are some results which hold no matter what. And then I had anticipated I would talk about some indirect interpretation. So what is coherence good for? Then we would all agree that we need it for quantum cryptography, we need it for quantum metrology. We just want to get some more quantitative statement here. And one answer that we have is coherence is good because it can be mapped one-to-one into entanglement. That's an indirect interpretation. And then entanglement is good because, as we have seen before, it's universally useful for a series of applications. How does this mapping work? This is already quite an old paper now. So suppose you have your system, and then you have an ancilla which is prepared in an incoherent state. We fix the basis from the beginning. So, and then you're allowed to do incoherent operations on system and ancilla. Of course, if your system is in an incoherent state, ancilla is incoherent, you do incoherent operations on both, what you obtain at the output is also incoherent. But not only that, it is actually provable that the output state is separable. On the other hand, if everything remains incoherent, so the ancilla is incoherent, the operations are incoherent, but your system has coherence, then what you get at the output can be entangled. And you can even show this as a theorem. So given a setup like this, you have entanglement between system and ancilla if and only if the initial system state has non-zero coherence. So every coherent state is useful to generate entanglement by means of incoherent operations with an incoherent ancilla, and then indirectly this makes it useful because that entanglement will be used for other applications. This is an indirect operational interpretation, can be made quantitative as well. In fact, you can define a family of measures of quantum coherence in terms of the maximum entanglement that you generate through this setup on your system. So coherence can be quantified as a potential for the creation of entanglement. Those of you who work in quantum optics will recognize a familiar pattern here because there's something very similar there about optical non-classicality of an input that is characterized as a potential for generating entanglement at the output of passive operations like beam splitters and so on. That's a very similar idea. But if we want to get some more direct operational interpretation without having to go to the bipartite case, what can we do? Let me first introduce a quantifier, which is again not new. It was borrowed and inspired from entanglement theory. And then I will show that this quantifier has a very nice and neat operational interpretation. So the robustness of coherence is the following. Basically, you start with your state, and then you try to mix it. So your state is rho. You want to mix it with another state, tau. And then you look at the weight of this mixing, little s, until the state that you get after mixing with proper normalization becomes incoherent. So the robustness is the minimum over all general states of this weight factor s, such that the mixture of your rho with state tau with a weight s becomes incoherent. So how much kind of mixing your state can tolerate until it loses its coherence. Similar definitions were used for other resources as well. So what you can prove, first of all, is that this quantifier is a valid monotone under resource theories of coherence, no matter which set you choose for free operations. It will work for all of them. And then we can show that this actually comes out as quantifying a certain advantage in a nice task, which I'm going to explain at the moment. So I introduce a task, and you don't see that it's related to robustness until the very end. The task is the following. It's about, effectively, it's a guessing game. So it's a channel discrimination, if you want. So what is the problem? We have a black box, and you can send a state in this black box. What happens in the black box? In the black box, you have a phase shift applied to your state. So it's generated by Hamiltonian H that you can write in this way, where the eigenvalues are J and the eigenbasis is the one that we adopt to define and quantify coherence in this case. And so this phase shift, the direction is known from the beginning, it's given by the Hamiltonian, but you don't know the angle. So your state enters and it is rotated along a fixed direction by a certain angle. What you know at the beginning is what are the possible values for this angle, and what is the prior probability distribution associated to each of the choices. So you have this setting, one of them happens, and then the state comes out. And then what you need to do is, of course, you have to come with a measurement that can infer some information about what has happened here. And so you have to give your guess. I think instance k equal 3 or k equal 2 has happened in this case. So this is a simple game. Your state is rotated by an angle which is one of a possible set that you know from the beginning, with certain probabilities. You just need to find out which one is it. Fine, so figure of merit for this problem is the probability of guessing correctly. Every time you define your initial set of possible phases and prior probabilities, then you're defining an instance of this game. Probability of guessing right is, of course, optimized over all possible measurements at the output. And then you have the expectation value of the corresponding POVM element on the state after this phase has been implemented, weighted by the prior probability distribution. That's it. Now you have two possibilities here. First possibility is you send in a state which is incoherent with respect to the generator of this phase shift. So this means that your state is diagonal in that basis J. And so when it comes in, the rotation has no effect because it's invariant under that shift. So rho out is the same as rho in. So once it comes out, there's no information imprinted on it. And what can you do in that case? You will cast your guess on the most likely outcome. So if your initial distribution of these probabilities was non-uniform, then you would just put your money down on the most likely outcome there. So for instance, you would just say that probability is the maximum over k of the prior probabilities distribution. On the other hand, if you send in a state with coherence, then whatever happens, it will be affected because it doesn't commute with that Hamiltonian. And so the question is, how better can you guess by using coherence with respect to not using it? So you can calculate the probability of success for a state rho, and then you can look at the ratio between that and the probability of success that you get for any incoherent state, and maximize this ratio over all possible settings of this game. Of course, you expect something bigger than 1, because coherence helps, so probability increases compared to using incoherent states. But the nice thing is that the actual advantage, so how much better you do by using coherence in this phase discrimination game, is quantified exactly by that measure which I had introduced before, the robustness of coherence. So you have a direct operational interpretation for a quantifier here, and it tells you that every coherent state is useful for phase discrimination. And the amount by which it is useful compared to states without coherence is given by a quantifier that can be defined independently. And it has this nice geometric interpretation. It's called robustness of coherence. So this was a result that we obtained a few years ago. And it was quite nice. I mean, people put it in the press releases and so on. And we even run experiments with it, generalized it to multi-level coherence and several stuff. But why should this be just the end of the story? I mean, is that something special about coherence, or maybe similar ideas can be applied to other resources as well? And then it seemed that few other papers came out more or less at the same time or a bit later, showing similar applications where, okay, you can establish an if and only if result for usefulness of some resource, and you can even establish quantitative results about the advantage enabled by that resource, relating them to quantifiers that are related to this robustness. And this was done for asymmetry, which is basically how much your state is not invariant under certain group transformation. This is also something related to metrology. And then steering is a stronger form of correlation than entanglement, and entanglement itself. So it seemed that there's something going on there. We can actually express a result like this for every resource theory, with the only requirement that the set of free states should be a convex set. So how does this result go? It is very, very similar to the one before. Yeah, still that time. Right. So let's assume we're talking about convex resource theory. So we are not giving specifics. So you can come up with just your own way of dividing states between useful and not useful, but as long as the set of free states is considered convex and closed. Closed means the limit of a sequence of free states is within the set. And then we have a general game, which is subchannel discrimination, very similar to before. We have an input state, there is a black box. Within this black box, you can have a finite set of possibilities, which will be expressed by subchannels that adapt to a completely positive trace preserving map. Just the sum of these subchannels. And then at the end, you come up with the measurement with P of M elements Mi. And your goal, as usual, is to guess which specific subchannel has occurred, maximize the probability of success that can be defined similarly to before for a given state, for a given set of subchannels, and for given output measurements by this expectation value here. Now, of course, this includes the case that we considered before, channel discrimination. If you consider each subchannel as a channel with a certain prior probability, then you can have a situation like the one before. Before, we had even more restrictions because the channel was unitary, but it doesn't need to be. Okay, so in this context, we can prove two theorems. One is the if and only if, so it's a qualification. And the other one is the how much, so quantification. Right, first theorem is in any convex resource theory, every state which is not free is useful for a subchannel discrimination task, in the sense that it yields a better performance quantified by probability of success compared to any free state. So this is the essence of every quantum helps, if you want. Mathematically speaking, any convex resource theory, a state is not free if and only if there exists a set of subchannels such that that state is better at discriminating them compared to any free state. In fact, the ratio between probability of success using your state compared to the maximal probability of success over the free state is larger than 1. And Lucas told me that this seminar has to be a technical seminar, so I included the proof. Then let's have a look at the proof. On one hand, one direction is kind of trivial. So if you find that this ratio is larger than 1, then for sure your state is outside of the set because that set is closed and you are dividing by the maximum of the set here. But then the more interesting direction is, suppose that your state is outside the set, can we always find a set of channels to discriminate such that you get an advantage there? And what we do, we have to construct them. And actually the answer is it's enough to just find 2 of them, because there will be a binary discrimination problem that works better with your state compared to any free state. And we construct these 2 channels. This will be qubit channels effectively. So they're projecting your system onto qubit basis here, and the amplitudes depend, the probabilities depend on expectation values of some operator x. Now, this operator x, do not have to enter into the specifics, but it's related to witnesses. If you're familiar with entanglement witnesses, in general, for any resource with the free set of states, you can come up with a hyperplane operator called the witness, which separates your set of states into two parts, one which contains a set of free states and the other which doesn't. And the witness is such that if your state is on the other side, it will be detected by that. Normally, we have witnesses such that the expectation value is positive on one hand and negative on the other hand. We can renormalize them in terms of an operator x, such that the expectation value is between 0 and 1 on this side, which includes the free sets, and it is strictly larger than 1 on the other side. So for your rho, it will be larger than 1 if it's detected by this witness operator. So we construct this pair of channels in this way, and now we have to calculate the probability of success in this case. Of course, it's a binary discrimination, so there is a well-known formula that takes into account the optimization of the measurements, and this is the formula due to Hellstrom. So the maximum probability of success for this binary discrimination is given by the Hellstrom bound that depends on the trace distance between these two subchannels that we have identified. Actually, these are actual channels with 50-50 probability. So it's a very simple discrimination task here. So you calculate it, and because of the properties of this X operator, then you find that if the state is within the free set, this trace distance is bounded. If the state is outside, it exceeds the bound. So if you plug everything in, then you find exactly that this is the case. So every time the state is non-free, there exist these two channels such that you guess better at discriminating between them two compared to if you use any free state. So every quantum helps in the sense every non-free state helps in discriminating pairs of channels. There's always exists a pair of channels that is better discriminated by your state. Right, so question is now how quantitative, how much better do you do by using this? And I think you probably already guess where this is heading to, because we were guided by this very, very neat example of coherence, and we already knew what we wanted to prove. So the answer is, again, going to be the generalized robustness. You can define generalized robustness of a resource, just like we did for coherence, minimum weight of a certain other state that you mix with yours until you lose the content of your resource completely, so you end up in a free state. If you want, this is important for the proof, you can rewrite this definition here in terms of a convex optimization. For some resources, this is a semi-definite programming, so it's easier to compute mathematically, like for coherence. For others, it is not. But in general, you can minimize trace of rho x, where x is an operator like I defined before. So it's non-negative, and the expectation value is bounded when the state is in the free set. So this means, look at these two definitions. This means, on one hand, that for the optimal decomposition, your robustness is equal to this weight S. Okay, once you find the optimal tau. From this other reformulation here, there exists some optimal witness operator X, that's like a dual problem, such that your robustness will be equal to trace of rho x minus 1. And we will use these two formulations in the proof. So proof of what? Proof of theorem 2, which says for every convex resource theory, the generalized robustness of resource quantifies now the maximum advantage in subchannel discrimination. So again, in formula, maximizing overall settings of the game, psi I are the subchannels, and overall measurements that you do, the ratio between probability of success with your state rho over the maximum probability with any free state is 1 plus the robustness of the corresponding resource. And I think now I probably can go through the proof. Yeah, let's have a look at the proof here. So there are, of course, two directions. If you want to show that there's an equality, then we have to show the two sides of the inequality. This one follows from the first definition of robustness, just the original one. As I said, in the best decomposition, there exists some state tau such that robustness is equal to that weight S, which means that rho is decomposed like 1 plus S sigma minus S tau, where S is given by the robustness. So if we calculate probability of success for rho, it will be, this is a linear function, so it will be probability of success of this bit here minus probability of success of this other bit here. And so it is low, it's bounded from above by just probability of success with the first bit here. And then probability of success with this specific free state will be, again, bounded from above by the maximum probability of success over all free states. And so you have that this statement is true for one direction in this case. For the other direction, then we have to use the convex optimization formulation. And again, this has to be constructive. So we will construct a set of subchannels and a set of measurements such that you show for the specific choice, you get the inequality here with the larger or equal sign. Again, we make use of the properties of this witness operator X, and then we consider sets of unitaries defined in this way, where these EJ are the eigenbases of our witness operator X. And so we will define our subchannels in terms of twirling over these unitary bases effectively. In this way, you can calculate probability of success for this specific choice of channels and measurements. It might not be the maximum, but it's already enough to show that it is larger or equal than 1 plus R. So you calculate it, it depends on this. On the other hand, as I said, from the convex optimization formulation, there exists an optimal X such that the robustness is just given by the trace of X minus 1.
Gerardo,
so you
I think I missed something.
Yeah.
Can we always make sure that these X exists? I mean, in every situation, for every system, I can always build an operator X like this.
Yes, because if it's from the Stone von Neumann theorem, you can always find, if you have a convex set with a convex subset, you can always find the hyperplane separating them. That's that defines the operator W, and so you can just renormalize it into the X. That's a general property of convex channel.
Okay. I see what you mean.
Again, it's crucial that the measure is convex, that the set of free states is convex. So it always exists.
Yeah, for sure. Yeah, without convexity. Yeah.
Without convexity, I don't know what, I mean, maybe for some other resources, there are some nice results, but we cannot get something as universal as this, unfortunately. Well, at least I don't know how.
Yeah.
Okay, and so for the optimal X, then this thing is proven, and this is it. Yeah. Right, so that's, I think, at most the technical bits which I had, but the message is clear. So whenever you can identify a subset of your states, which you can call free, and it's a convex set, then anything outside of that set will be useful for something. And the advantage it enables, this something is, we have identified the universal framework for this something, which is in terms of discriminating channels. And the advantage you get by using any state outside of your free set compared to states inside of the free set is by itself an operationally motivated quantifier of your specific resource, which is related to the robustness of the resource. Right, so there's been some extensions and developments since we published this result. And there were some which were kind of parallel, and it's nice because, of course, the whole talk I was talking about resource theories of states, but you can have a more general study of resource theories for channels and measurements. So you can have dynamical resource theories, which look at classifying the resource value of the operations itself rather than states and what you can do with the operations. And so there's been kind of complementary results which show again that you can quantify how useful a channel is in terms of its power for discriminating states and vice versa. So all of these papers, they kind of establish variations of this theme, extending it to resource theories of channels and measurements as well, always connecting some resource power in discriminating tasks with some generalized robustness of the associated resource. And then there is this more general paper by my two former collaborators, which even generalizes these works beyond quantum mechanics. So they look at GPTs, and then they show that it's possible to to characterize discrimination tasks in generalized probabilistic theories, and then to find quantitative statements about advantages and specific measures of robustness that they can define. So this is not even every quantum helps. I would say every, I don't know, maybe every non-classical or every non-free helps in discrimination problems. And finally, I want to mention, I would say discrimination problems are tasks which are of practical relevance. You just need to distinguish between a preset of finite possibilities. It's a kind of discretized version of parameter estimation, which is what we normally want to do in metrology as well. But the question is, can we actually generalize these results to the continuous case of estimating parameters rather than just distinguishing between presets? And the answer is yes. So I do not want to go into too much detail about this because you had the previous talk, but I want to link to the previous talk. So the previous talk you had in your series was by Luis Davidovich, and he talked a lot about quantum metrology there. So he gave you all the general introduction about the framework. So I can just briefly mention the case of single parameter, just to make sure we all remember what are the figures of merit there. So the idea is you want to estimate a parameter which is imprinted by some transformation on your state. So you have a probe state, goes into black box again. But now we do not have a preset of possibilities. We just know that some channel is happening there, which depends on a parameter. And you want to estimate the value of this parameter by, again, coming with a measurement and then forming an estimator, which is probability distribution for your guess. You can repeat this experiment many, many times. And then, of course, you form enough data that will help you narrow down the error on guessing the parameter. And there is a fundamental bound, which you all know about, is this quantum Cramer-Rao bound, saying that the variance in estimating this parameter is bounded from below by statistical factor 1/nu, which is number of times you repeat here, but then the inverse of the quantum Fisher information, which I don't even define on this slides because you all know what I'm talking about. So this quantum Fisher information would become a figure of merit for the precision of estimating your parameter, which would be like the counterpart of the probability of success in the previous discrimination setting. What we can do, again, we can consider our sets of states divided between some free states and some non-free states. And then you can look, is any state which is non-free useful for metrology? We know it's useful for discrimination, but is it also useful for estimating a parameter? So you can define an advantage in this case by instead of the ratio, we can look at the difference if you want. Fisher information on a metrological problem calculated from your probe state row minus the maximum of the Fisher information for all possible free states. And there have been a few developments in this direction recently. One of them was actually a paper that I did with some other colleagues in my university and beyond. This was a different paper about resource theories where we were looking at the problem of determining whether entanglement between identical particles is a resource or not. Because in the past, there's been a lot of debate whether particle entanglement is real or it's a real entanglement or it's just a consequence of symmetrization principles. What we did here, we constructed the resource theory for it. So we found some consistent way of defining states which are or not entangled, and we gave an interpretation to it, again, direct and indirect. Indirect, you can sort of activate this particle entanglement and distribute it to entanglement between physically distinguishable particles, which was something that was already proposed by Martin Planey and this group, but we found that doing this by means of free operations in our resource theory is a consistent way of making use of the identical particle entanglement. But on the other hand, we were looking at how to quantify usefulness of this in specific contexts, and we all know that, say, entanglement between identical bosons is useful for metrology. Spin squeeze states perform better than spin coherent states for estimating phases. And what we found is that the quantifier like this is actually a monotone of the identical particle entanglement in our resource theory. So the metrological advantage is clear in a specific resource, which in our case was identical particle entanglement. Of course, very similar result, but more general, was produced by Bartosz and his new collaborators in Singapore. And I think this one would be the direct counterpart to the theorems that I presented before. in the sense that it's another, every quantum helps, but in this case, it's in the context of metrology. Again, if you have general resource theories with convex free set of states, there will always exist, for a given state, there will always exist some particular parameter estimation problem such that the quantum Fisher information minus the quantum Fisher information on free states is strictly positive, if and only if your state is outside the set of free states. So every state is useful for some estimation tasks. There always exists some problem for which your state gives you better Fisher information, and here's also the classical Fisher information. It gives you better Fisher information than by using free states. So it's again a case of finding what your states are good for, because they will always be good for some. So if I have to conclude, I would say at this point, general message that we give is, I think I'll put this quote. This quote is found often attributed to Albert Einstein, but I don't believe it's true. Probably it's one of those fake quotes you go, but it captures the idea. So this series of papers show one thing. Every quantum resource, in the sense that every state which is outside of a properly defined set of free states, is actually useful for something. You just need to find it. Yeah. So if you start from a given task, then you can look for what are your resources to do that task properly. That is one problem. On the other hand, if you just start from any state that you might consider to be not free, then you can rest assured there's always existing a task. And we show two examples. One is for the context of phase discrimination. The other is in the context of parameter estimation. So there always exists some particular task such that your state will perform better than all the free states. So whether this helps addressing the needs of quantum technology industry at the moment, it is not clear. I think there's a lot of work that still needs to be done for starting from more tailored restrictions and needs, and then finding out what is the best in situations which deviate from ideal nice situations like this before. But at least it gives some kind of comforting answer to the question whether every quantum resource is a resource or not, and the answer in the specific context that we have presented seems to be affirmative. So I think I would probably stop here and answer any questions you have.
Okay, Gerardo, many thanks for the talk. It's really interesting. I have some questions, but I would like to let the audience. I mean, if somebody, Daniel Jonathan, please.
Hello, hello.
Hello.
Not sure you can see me.
I can see. Yes.
Yeah.
Okay, I can't see myself. We don't use Zoom a lot. Hi, Gerardo.
Hi.
That's an incredibly beautiful result. It doesn't say anything about comparing different states, right? So if every state is good for something, but you don't say you don't say, for instance, if one state is more useful than the other for most things. Can you extend this kind of very general picture to some kind of classification? Or is
you can be, yes, because you can, because of course so I have these two results. One is, okay, it's an if and only if, but the second result, it's linking with the quantifier. Yeah, so we are saying that every state, the advantage that you get in this task compared to the use of free states is quantified by a specific measure, which is a valid monotone in your corresponding resource theory. It's given by the robustness. So this suggests that you can classify the resource power of your states in terms of the single letter formula, which is given by the corresponding robustness. Yeah, so the state with the highest robustness will be the most useful because that's the one that gives the most advantage compared to non-free
But they're useful for possibly for different tasks, right? Because there is some task for which they're useful.
You're right. Yeah. So for every state, there is the setting in which they shine the most. Yeah.
Yes.
Yes.
But you don't. but I mean, that opens lots of possibilities. I mean, I'm wondering.
It does. It does. Yeah, it does.
So there will be some resource theories where there is a universally useful state. There will others will maybe not. There won't be. And
you're right. You're right.
Can you explore in these generic terms? And what I'm saying is that this generic framework may help identify different classes of resource theory where the comparisons between different resources has different structures.
Yeah, and I think this is a very interesting problem that needs to be done. So because you can have so for instance, at the moment we can even have, you can divide your states in different ways, so that one state that is maybe maximally resourceful in one resource theory is actually free in the other. And this is the most trivial example is just with coherence itself. If you pick different bases, you have a completely, so if you have the plus state is maximally coherent with respect to computational basis, but it is free with respect to the eigenbase of sigma x. Yeah. So once one of those would be maximally useful for phase discrimination if you're rotating this way, but not useless if you're rotating this way. So what is interesting is to consider multiple resource theories at once, where you maybe have competing constraints like this, and try to see if we can establish more complex hierarchy. That's very interesting problem.
Sort of what I was thinking.
Yeah, I don't have results at the moment, but I'm sure if I get a new PhD student, I'll call you and we can work on that. Yeah.
Fine. That was great. Thank you again for the talk.
Thank you.
Okay, thank you. I think Belita raised your hand.
Hi.
Yeah.
Please.
Hi. Nice talk. I learned a lot from it. I wanted to ask you something about the hardware of the CPUs. You mentioned the Google chip, which is based on superconducted loops. What's the Chinese hardware?
I think they have two different things. I think the one I showed is also superconducting loops, but they have a bit more qubits. I think they have like 60, 65. Then they also did something else, which is based on integrated optics, and they did Gaussian boson sampling on it. So they have different technologies. Superconducting qubits are still the ones for discrete variable systems. They still to be, at the moment, the ones which have been scaled up the most, up to this, let's say, less than 100 qubits. On the other hand, then there is some integrated optics. They basically what they do, they design linear optical circuits just by lithography on pieces of glass, and so they can have multi-photon experiments for Gaussian boson sampling. And this is what they also did on a different paper where they demonstrated, they claim supremacy for over 70 photon experiments there.
What's the group that's doing that?
The main person is called Zhang-Wei Pan. He's kind of, the most powerful Chinese researcher. And then he has two laboratories. One is in Hefei and the other one is Shanghai. So he has multiple affiliations there. Whatever they're doing, it's him involved.
It's the leader now.
Well, it's been for a while, yeah.
Yeah.
They even launched these satellites for global communication.
Yeah. Okay, thank you very much.
Thank you.
Okay, do we have more questions here in the audience?
I have a question. I have a question from the YouTube. So,
okay.
Guilherme is asking, he's thanking you for the talk, and he's saying, would like to know if there are ideas of using resource theories in the context of quantum computing. For example, if one could use those ideas in quantum error correction.
Thank you. So who am I speaking to? I don't see anyone.
Oh, it's me, but it's a question. It's Thiago. But it's a question that is coming from YouTube.
Okay, sure. Right. So yes, that's a very nice question. I think there's been an active investigation about the resource behind quantum computing, and some of these results apply quite nicely. I think even in our papers we mentioned it very explicitly. We got some results for the resource theory of magic. So of course contextuality, which in some cases is equivalent to magic, is a resource for measurement-based quantum computation. So our results directly apply to that, showing that every state, which is not in this, in that case, it would be every state, every contextual state is a resource for magic state distillation. For quantum error correction, I'm not sure if we know exactly what is the resource, but it would be nice. Yeah, at the moment, most of these applications, they seem to be tailored towards sensing and metrology. Discrimination, estimation, they are all within the same, I would say, within the same branch of quantum technologies. I would prefer if we can find applications which are working more towards benchmarks for quantum computing and like quantum error correction problem. At the moment, we don't have a framework like that, but I think it can be worked out.
Okay. Norton also had a question into chat. I don't know if
I've read it. Yes.
Okay.
So Norton asks, the focus has been given to entanglement, but what about quantum discord? So quantum discord has been shown. So we have several papers over the years, as most of the community in Brazil probably knows, about quantum discord and specific applications where it is shown that quantum discord provides advantages. And there are also applications in the context of quantum metrology. In that case, it's slightly different because we are looking at estimating parameters in a worst case scenario where we do not know the direction in the first place. So all these applications I was telling you, we fix the basis, or we fix the Hamiltonian, or we fix the class of channels, we just want to estimate or discriminate the phase. Quantum discord becomes useful where in principle you do not even know what is the generator of your transformation. And so you need to have a quantum discord in order to be able to accomplish this discrimination or estimation in the worst case scenario for whichever. So when you minimize the quantum feature information over all the generators, then you get the advantage quantified by quantum discord. I cannot frame it as generally as these results for the simple reason that the free states, which are the classical quantum states, the ones without quantum discord, they do not form a convex set. So strictly speaking, I cannot apply these results, but we have obtained specific results for discord in discrimination estimation, even with experiments that we have done in Brazil, actually, with Ivan Oliveira, Bert Satur, Diogo Soares Pinto involved as well. So that's my answer to Norton.
Okay, this also applies for contextuality, no?
Yeah.
Yeah,
It does.
is the same reason? No? Yeah. Okay, do we have more questions here in the audience? Sorry?
I mean, I have a kind of question or comment, because I mean, in the beginning, I have this sense that at the end, I mean, the task, I mean, when you go to coherence, you know, as you were talking with Daniel, I mean, in every base you have coherence, you can find a task what coherence in that base can be useful. But it seems very specific, you know, because you have a state, you have to find a very specific that state is able. So, but and then I mean, you're trying to give the message that you shouldn't try to find that the state is good for everything. No, this is stupid somehow. No, that's a message I think you're saying.
This is not my quote, but yeah. So what we're saying is that, yeah, if you have a fixed task, then you'll always find that some states are not good for it, but they will be good for something else.
But I was thinking about, but I was thinking about the idea, I mean, something that interests me more is like, if you're talking about macroscopic coherence, no? That's where I think if you go to the classical and the quantum border. So I think that like in the coherence, another way to see this instead of tasks is to look at which observable you're gonna be able to see the effects of this coherence, like some interference. No, you're gonna see the difference between having a true coherence state or just a mixture of a classical mixture of states. So, and I think that when you go to the macroscopic regime, finding this observable, measuring this coherence, it gets harder, you know? So I would think that in the case that you are doing this discrimination, the observable, no, the P of M that you have to implement to find this phase estimation is always going to be hard to implement as you go to macroscopic limits.
That's a very good question. I don't know. We have to look at the cases. Yeah, I don't know. It could be. It could. Of course, this, as you see, is a mathematical result. We have done some experiments, but these experiments were done with up to 4 photons. So there we could construct explicitly what was the optimal POVM, and then these people, they could implement it. But I would guess that it becomes complicated. Of course, one can always, this is done also in metrology. While we know for sure that the quantum feature information is always the best, and typically depends on, it's realized by measurements on some basis of the symmetric logarithmic derivative, that is not always easy to implement. So what people look at is try performance of something that people can realize in the lab, say homodyne, heterodyne, and see how close we get. So this type of approach, we can always get the absolute best, and then we can go and try some feasible POVM and see how close we get. So even though they do not saturate the maximum advantage, then they would still probably be able to show some improvement compared to the corresponding free states.
Okay, yeah. Because this is also be a question when you try to implement this on quantum computation, no? Because there you want some kind of macroscopic coherence, no? A microscopic one would be useful at all.
Yeah, there's still a lot to do to make this really useful in practice. At the moment, I like the mathematical side of it. I'm from the School of Mathematical Sciences, but they do not answer the initial question in practice, I think. But still nice.
Okay. Do we have more questions in the audience or in YouTube, Thiago?
No questions in YouTube. No.
Okay, then if you do not have any questions from the audience and on YouTube, I think we can. What is your father? Oh, okay. I think we can simply thanks Gerardo again for a very nice talk.
Thank you.
Thank you very much for accepting our invitation, Gerardo, for being here virtually today, and I hope that we can host you in person very soon. Thank you very much for everybody coming here. And just remember that in 2 weeks from now, we have Paulo Henrique Soto Ribeiro for the next talk. Thank you very much. And somebody send greetings to Fabrizio.
I have not seen him in many years.
Okay.
Yeah. Thanks, Silaket. I have not seen him in a while, actually. Yeah, but I will whenever I see him again. Fabrizio is my former PhD supervisor. It's good friends with many of you as well. Thank you.
Thank you very much. Thank you very much to all of you.